Hi students, in this lecture I am going to discuss electromagnetic induction. Let us see. So first focus on the list of concepts. So first we discuss magnetic flux, then Faraday's law, Lenz's law, motional EMF, induced electric fields, self-induction, mutual induction, combination of inductors, RL circuits, and finally LC oscillations. So let us see first what is magnetic flux. Okay, if you remember while discussing Gauss law, so first we have discussed electric flux, and that we have discussed that electric flux is a measure of number of field lines through a given cross section area. That means if flux is more, that means more number of field lines are passing through that surface. Now here also exactly the same thing. So it is defined as magnetic flux. It is a phi suffix b. It stands for magnetic flux. That is defined as integral b bar dot dA bar. Means how to calculate magnetic flux. And that is given by integral b bar dot dA bar. Suppose if a field is uniform and area is now it is a plane, means it is a plane surface. In such a case, this becomes b bar dot a bar. Okay, so this is equal to b into a into cos of the angle between those two. So which is a scalar quantity. And from this we can guess units of magnetic flux. So we are knowing for B it is a Tesla, and for area meter square. So units will be, it is a Tesla meter square, or same thing it is written as Weber. It is name of a scientist writing as W capital and small v. Okay. So if you are taking a surface, if more number of magnetic field lines are passing through this surface, then we say flux is more. Okay. So more flux means more number of field lines passing through surface. Right. Let us now focus how to solve basing on these problems. Let us take a simple problem. A long straight wire is carrying current along positive z direction. Find the magnetic flux through a square loop which is xy plane. So it is given that long straight wire is carrying current along positive z direction. Okay. So we have to calculate now magnetic flux through a square loop which is in xy plane. See how to calculate that. Suppose it is given along z axis. Let us take this board plane as xy plane. So we are taking now board plane as xy plane. So current is now it is outwards because it is given along z direction. Means wire is normal to plane of this board. It is now given a square loop. not mention exact location. Let us consider it is now loop. So here our intention is that magnetic flux zero or non-zero. It is not about the value. So now you can see because of this current carrying wire, field will be, it is a concentric circles. See how is that? So take right hand. So keep the thumb of your right hand along the current flow. Curl fingers. Now curling fingers. They will be anti-clockwise. I am showing here. This is what we have learned in the previous chapter, right? Magnetic field due to current. So magnetic field lines will be now concentric circles. That means you can see if you take a tangent at this point, that tangent gives us direction of field at that point. So these are now concentric circles. Okay. So here what we can say is magnetic field due to this long wire is confined to this XY plane. That means it is only in XY plane. In such a case, coming to the square loop, we have learned that for a plane surface, direction of area vector is normal to that plane. That means it may be outward normal or it may be inward normal. And generally we are taking outward normal as positive. So if I am taking outward normal as positive, for this one, direction of area vector. For area vector, direction is now, if I am taking outward, it is a k cap. It is along positive z axis. And we have seen that because of this wire, field is only confined to xy plane. That means between B bar and A bar angle is 90. And we have learned that calculation of magnetic flux. It is integral B bar dot dA bar. Now in this case, B bar confined to xy plane. Direction of dA bar, it is along positive z direction. Or if you take along negative, minus k cap. So here between these two vectors, angle is 90. That means there is no magnetic flux through this loop. There is no magnetic flux through this loop. That means no magnetic field line is passing through this surface. The meaning of flux equal to zero. Okay. Right. Let us see the next problem. A uniform magnetic field 2I cap plus 3k cap Tesla is present in the space. Find the flux through a circular loop of radius r, which is in xy plane. You can see carefully given circular loop. Radius is r, it is in xy plane. That means for this circular loop, if I am taking area vector, for that area vector direction will be either positive z axis or negative z axis, right? And coming to field 2I cap plus 3k cap. Let us see now. Given field is 2I cap plus 3k cap. That means the field is uniform. 2I cap plus 3k cap. Coming to the circle, right? Circle of radius r, which is in xy plane. Let us take this board plane as xy plane, which is in xy plane. So if I am taking normal to this plane, that means direction of this area vector. which is a completely our choice. I am taking this as outward normal as positive. That means direction of area vector. It is now k cap. Okay. So it is now a plane surface. And here field is uniform. So if you want to calculate magnetic flux, integration is not required. Directly B bar dot A bar. Okay. Because it is a plane surface and field is uniform. Substitute values in this. It is a 2y cap plus 3k cap dot A bar. Coming to it is a circle. Area is now pi r square. Direction I have taken outward normal. So it is a k cap. Then see what we get. I cap dot k cap 0. K cap dot k cap that is 1. So it is now 3 pi r square. Okay. And here we got flux is a positive. That means here field lines are coming out of this surface. Is a pointer. Here field lines are coming out of this surface. That's why we got here positive. Right? Let us see now the next concept. It is the Faraday's law. Let us see what is it. Right. So coming to Faraday's law, which is based on experiments. So I'm taking here one coil. It is a conducting coil. And in that we are inserting one galvanometer. So I'm taking here one galvanometer. So first we have taken one conducting loop and we are attaching here one galvanometer. Now here what we are doing is, so we are taking a magnet. Suppose this is North Pole and this is South Pole. When this magnet is moved towards the loop, it is observed a deflection in the galvanometer. That deflection indicates there is a presence of current. That means without moving the conducting coil, if magnet is moved towards the coil, then it is observed that there is a flow of current in the coil. Now, if the same magnet is moved away from the coil, then they observed that deflection is now opposite. That means direction of current is opposite to the previous direction of current. So first of all, we are moving the magnet without moving the coil. Next, the same thing repeated by keeping the magnet at rest and the coil is moved towards the magnet. Again, a deflection is observed in the galvanometer. That means there is a flow of current. Now, the same coil is moved away from magnet. Then also a deflection is observed in the coil, but it is opposite. So from these experiments, so he gave a conclusion that whenever the magnetic flux linked with a closed loop, or you can say conducting loop, is changing, then current flows in that. But remember, to have flow of current, there must be a battery. But in this, there is no battery, but still current is flowing. That means because of the relative motion between the coil and the magnet, there might be an EMF induced because of which current is flowing. Now from Faraday's law, we are giving that an expression for the EMF induced. So according to Faraday's law, the EMF induced is given by negative of the rate of change of magnetic flux with respect to time. This is Faraday's law. So it is saying that whenever the magnetic flux linked with a conducting loop is changing, then current flows. But we are knowing that to have current flow, there must be a battery because battery provides an EMF. But here there is no battery. That means we have to understand that because of relative motion, an EMF is induced because of which current is flowing, and that EMF is given by negative of the rate of change of magnetic flux with respect to time. Okay. Let us see now how to use this to solve problems. And before that, we focus now direction part. And for direction part, we are focused here Lenz's law. Let us see what is Lenz's law. Its only purpose is to specify direction of induced current. And this is simply basing on conservation of energy. Let us see in detail. So we have taken here one coil, right? This is one coil and this is now magnet. Suppose north pole is facing the coil. You can see when it is moving towards a coil, the face which is facing this north pole that acts as north pole. So that north pole and this north pole now having repulsion. So if you want to move this magnet, we have to do work to overcome this repulsive force. And the work which is done because of that current flows in the coil. That means we are getting now electrical energy. So we are doing work in moving the magnet. And that work is now reflecting here in the form of electrical energy, means current is flowing. Suppose if you think in the reverse way, like if this is north pole, now this is becoming south pole. Just assume what happens if this is a south pole. So here what I am saying is, for example, we are placing this magnet on a smooth surface, which is a horizontal. See carefully. I am placing this magnet on a smooth surface, which is horizontal. Now I am just pushing this magnet towards a coil. That means kinetic energy is given to the magnet. Let us assume the face which is facing this north pole is becoming south pole. Then what happens is because of attraction between this south pole and north pole, it will gain speed. That means it moves with acceleration. That means its kinetic energy keep on increases. So here what we have done, we have just pushed it. Means we have just given some kinetic energy to the magnet. But now what happened? If this acts as south pole because of attraction, its speed keep on increases. Its speed keep on increasing means its kinetic energy keep on increasing. And because of relative motion, here current flows. That means we are getting electrical energy. But remember, here kinetic energy keep on increasing and here we got electrical energy. That means sum of these two energies is greater than the energy what we have given, which is violating conservation of energy. Getting it? That's why this phase becomes only north pole. This cannot become south pole. That means when magnet moves towards a coil, if this is north pole, this becomes north pole. So this becomes north pole means this is now here current flows it is anti-clockwise. Okay. So in that way, we can decide direction of current. For example, in the same experiment, if magnet moves away from coil, this is now north pole. Okay. It is moving away from coil. Then see what happens. When it moves away from coil, this phase will become south pole. This phase becomes south pole. So that this will attract now this north pole. That means if you want to move this magnet, we should do work. And that work, because of that work, what happens is current will be produced or current will be induced in the coil. So since we are doing work, we are able to get here electrical energy. Okay. So like this, we can decide. Means if it is becoming south pole, that means when it is moving away from coil, this phase acting as south pole means current flow will be clockwise. Okay. And see here the statement what we are giving. The direction of induced current is in such a way that it opposes the cause of its production. Now see the example carefully. In the first case, current is induced, and for that current induced, the cause is motion of the magnet towards the coil. That is a cause. So now what Lenz'S says that it opposes. Here it means the induced current opposes the direction of induced current is in such a way that it opposes the cause of its production. So current is induced because of motion of the magnet. It is opposing that a cause. That means it is opposing motion of the magnet. That means in this case, it has to repel this one. It has to repel means this should become north pole. Okay. Now see the second example. Here, cause of the production of induced EMF or induced current is motion of the magnet away from coil. Right. And according to Lenz's law, direction of induced current is in such a way that it opposes the cause of its production. Now the cause is motion of magnet away from coil. It opposes that. It opposes that means if it becomes south pole, then this will attract this north pole. So force acting on this is left side, opposing its motion. Okay, let us see once. Coming to Faraday's the statement. The EMF induced in a closed loop is equal to the negative of the rate of change of magnetic flux through the loop. Okay, that is now statement. And this negative sign is for direction part. Let us see now Lenz's law. The flux of the magnetic field due to induced current opposes the change in the flux that caused the induced current. Okay, and I'm saying like the direction of induced current is in such a way that it opposes the cause of its production. So both are same. See once carefully. The flux of the magnetic field due to induced current opposes the change in the flux that causes the induced current. Okay. It is a consequence of conservation of energy. This is about Lenz's law, right?